So what if we had a different transfer function, right? Previously, right, we were assuming that we had a transfer function that looked like this. So the most basic case. What if we had a slightly more complex loop filter function? So if it's changed to a higher order, s plus a over s, then right, this is going to go into here. And we also know that there's this final value theorem that can help us figure out what the limit of this is in the limit. Okay, so if we place this in, right, we're going to substitute this in for our loop filter function, and then this has not changed, right? This is still the same, right? For the case where we receive something that has some slightly different frequency and slightly different phase, we want to figure out what the error is going to be in the limit if we have a different transfer function, a different filter function. So we can apply this final value theorem, which says that as s goes to 0, s times f of s is equal to the limit as t goes to infinity. So multiplying all of this by s, we can now see that we're going to get this for our final value theorem. And we see that based on that, where we have the error in the s domain as this for our new transfer function, we multiply through, and then we see that we are going to get down to 0 in the limit, right? So when this gets multiplied by here, right, this is going to create a power of 3 on top, and so as that goes to 0 here, that's going to force everything down to 0 as well. It's going to go down faster in the numerator than the denominator. There's some more mathematics you could do later on your own, but basically we can probably intuit that this is what the limit is going to be. So for this case, right, we change the transfer function, we increase the order of it, and when we increased the order of it, we now see that our error is down to 0 instead of having that constant, right? Previously, we had a constant like this, but now we're down to 0 when we increase the order of our transfer function. So going back to the time domain for the higher order loop, final value theorem says that the error is going to be equal to 0. And again, we can have that rearrangement where we know that the output is equal to the input minus the output error. We know that in the limit, right, our output error is equal to 0. That's what we just use the final value theorem for. Therefore, the output phase and the input phase are going to be identical as you have this time approaching infinity. It's going to have the same input to the loop and output from the VCO. So substituting in for a higher order loop, as time approaches infinity, the output from the VCO can be simplified down to this omega 0 plus phi 0, and these are exactly the same as what the input was when the input had some deviation, right? These input had some deviation from your omega c. So when your input has some deviation from omega c, the free running VCO frequency, and you have a higher order filter, you can reach the point where there is no phase error. Now, all of these, so far, we assumed that we basically received something, right? We received this signal, but we also assumed, and we didn't really talk about this, but that we assumed that these were not changing with time, right? We are receiving this, but this is just some constant. This frequency is not changing with time at all. But what if it was? Okay, so if you were to use small error analysis, first order loop will not work. So if your incoming frequency is changing with time, a first order loop will not actually, you will never get the VCO frequency to match your input. The second order loop would have a constant phase order, and the third order loop would have a 0 phase error. So again, this would only be true if for the small amounts of error. So when this would basically only be true when this minus this is a pretty small number, leading to a small phase difference. Only under that condition can linear analysis be applied with, and it also kind of implies that the input frequency is not that different from your VCO frequency to begin with. if you wanted to actually analyze these, right, for different times when these are not so close to each other, you would have to use nonlinear models for the general high order case, and this is quite a ways outside of this class and would be covered in some kind of controls class, probably at the graduate level, or some advanced microwave or phase lock loop class.